You look up at the sky and see thousands of stars, and your brain quietly assumes someone has to be out there, and probably close. But when you actually run the numbers on distance, time, and what we can really detect, a much colder picture appears. One where our part of the universe might be full of planets and still completely empty of minds like ours. In this video, we're going to zoom out, step by step, and ask a simple, unnerving question. Not, is there life out there, but is there anyone even remotely near us at all? But before we continue, please subscribe to the channel to give your support. Let's continue. Right now, you live inside what physicists call your observable universe. That's the region of space from which light has had enough time to reach you since the Big Bang, about 13.8 billion years. Because space itself has been expanding while light travels, that region is not 13.8 billion light-years in radius. It's about 46.5 billion light-years in every direction. In straight numbers, that makes the diameter on the order of 4.4 times 10 to the power of 26 kilometers, and about 2.7 times 10 to the power of 26 miles. That is the part of the universe you can ever, even in principle, receive information from. Here's the hard part. Anything outside that radius is not just farther away, it is cut off from you forever. Not because you do not have good enough rockets, not because you do not have a big enough telescope, but because there has not been enough time since the beginning of the universe for light or any other signal to get from there to here. Those regions are what physicists mean when they say causally disconnected. No signal from you can reach them, and no signal from them can reach you, no matter how long you wait. So even before you start asking, is there life out there? Physics has already drawn a hard boundary around which out there you can ever interact with. But even inside that boundary, your usual sense of distance breaks down. On Earth, you use kilometers or miles, maybe a few thousand at most. In space, the basic unit is the light year. A light year is the distance light travels in 1 year at about 300,000 kilometers per second, around 186,000 miles per second. Multiply that speed by every second in a year, and you get about 9.46 trillion kilometers, roughly 5.9 trillion miles, for just 1 light year. That is the standard step size once you leave your solar system. Now compare that to something that does feel small to you, the distance from Earth to the Moon. That is about 384,000 kilometers, around 239,000 miles. In spaceflight terms, that is close. We reached it in a few days with 1960s technology. If you take that Earth-Moon distance as a basic unit, then 1 light year is like doing that trip back and forth about 24 million times. So when you hear that the nearest star to the Sun, Proxima Centauri, is 4.24 light-years away, you are not talking about the next star down the road. You are talking about a separation of roughly 40 trillion kilometers, around 25 trillion miles. That is the easy neighbor. So here is the question that starts to hurt. When one single step in your map is trillions of kilometers, what does near even mean anymore? On human scales, the difference between 10 kilometers and 1,000 kilometers is huge. On cosmic scales, the difference between 10 light-years and 1,000 light-years is still tiny compared to the size of the galaxy. Your language was not built for these numbers, but the universe does not adjust itself to make your words comfortable. And distance in space is never just about how far. It's always also about how long ago. On Earth, when you look at a building, the time delay from that light leaving the wall to reaching your eyes is so small you can treat it as 0. In space, the farther away an object is, the older the image you see. When you look at the Sun, you see it as it was about 8 minutes ago, because light took 8 minutes to cross 150 million kilometers, about 93 million miles. When you look at the Andromeda galaxy, you see it as it was about 2.5 million years ago, long before your species appeared. When we look at some of the most distant galaxies, we see them as they were more than 13 billion years ago, when the universe itself was young. Because the universe has been expanding the whole time that light has been moving, those galaxies are now much farther away than the distance that their light has traveled. That's why the current radius of the observable universe is 46.5 billion light years, even though its age is 13.8 billion years. Space has been stretching, so the gaps between galaxies have grown while the photons crawl across. So every time you look far, you're not seeing the universe now. You're looking at a set of time slices, stacked by distance, with the oldest ones at the edge. That raises a direct problem for the idea of neighbors. To really share a present with someone, you both need to be close enough that light can travel between you in a time that actually matters to you. On Earth, that might be milliseconds or seconds. In space, if a potential civilization is 1,000 light years away, any message you send takes 1,000 years to get there and 1,000 years to come back. If they have already gone extinct in the meantime, you're just shouting into their past. You never share a moment with them. You're always out of sync. Physicists use the term light cone to formalize this. Picture all the points in space-time that can send a signal to you or receive one from you, moving at or below the speed of light. Put them together and you get a kind of cone-shaped region in a space-time diagram, expanding outward as time passes. Everything inside that light cone is in principle something you can affect or be affected by. Everything outside it is forever unreachable. That's not a technology limit, it's a structure of reality limit. So when we talk about who might be out there, the real question is not does life exist somewhere in the universe, it's how many of those lives fall inside your light cone at the same time you exist. And now add one more twist. Even within your observable universe, some regions are only just now becoming visible. Light from them is arriving at Earth for the first time in cosmic history. Others are right at the edge, so stretched by expansion that future light they emit will never make it here. Over very long timescales, more and more of the universe will effectively drift over a horizon and vanish from possible contact. The set of places that can ever know you exist is not only limited, it changes with time. So when you step back and look at all of this together, the statement, "maybe there is no one near us," is not a dramatic, lonely line. It's the default prediction once you combine huge distances, the finite speed of light, the expansion of space, and the fact that civilizations have to exist during overlapping time windows to actually talk. Physics does not guarantee neighbors. It almost guarantees the opposite, that most intelligent life, if it exists, will be too far away in space or too far away in time to ever share a conversation with you. And that's before we even bring in the next constraint, the strict speed limit that locks all of your travel, all of your signals, and all of your dreams of meeting someone else into a narrow range of possibilities, and turns even the nearest stars into almost unreachable targets. You don't just live far from everyone. You live in a universe that enforces a strict speed limit on every signal and every ship you could ever send. That limit is the speed of light, and it's not a suggestion. It's built into how space and time work. Light in a vacuum moves at about 300,000 kilometers every second. That's around 186,000 miles per second. In one heartbeat, light could go from Earth to the moon and back. To your everyday intuition, that sounds basically instant, insanely fast, almost like infinite. But across interstellar distances, that speed starts to feel painfully slow. This isn't just about light itself. According to special relativity, nothing that has mass can reach that speed. The closer something with mass gets to light speed, the more its energy requirement explodes. You don't just need a bit more fuel, you need ridiculous amounts more, until it becomes effectively impossible. So every rocket, every probe, every starship you can realistically build has to stay under that 300,000 kilometers per second ceiling. And because information can't move faster than light either, no signal can beat that limit for a message. There's no known loophole here, no confirmed warp drive, no hyperspace lane. People write science fiction about those things, but in actual tested physics, nothing has broken that rule. So you might say, fine, light speed is the max, but it's still huge. Surely that's enough to keep the universe feeling connected. That sounds reasonable until you point that speed at the distance to the nearest star and watch the numbers crush that hope. The closest star to the Sun, Proxima Centauri, is about 4.24 light-years away. In kilometers, that distance is around 40 trillion. In miles, about 25 trillion. This is the next door star on a galaxy map, the easiest real target beyond our own system. Now compare that to the speed of something that we actually flew. Apollo 11, the mission that took humans to the moon, left Earth at around 40,000 kilometers per hour, about 25,000 miles per hour. That's far faster than a commercial jet. It's a serious high-energy trajectory. If you took that Apollo speed and just pointed it straight at Proxima Centauri with no slowing down, no course corrections, nothing fancy, the trip would take on the order of 100,000 years. That is longer than all of recorded human history by a huge margin. Even if you use a faster probe, like the Parker Solar Probe, which can hit over 600,000 kilometers per hour when it dives near the sun, you are still talking thousands of years for a single trip. On top of that, you have to think about acceleration and deceleration, because you cannot just slam a human crew from 0 to a huge speed instantly without hitting them with lethal g-forces. So the nearest star is, in human terms, another country of reality. It sits in the same galaxy, it follows the same physics, but on your lifetime scale, you do not go there and you do not come back. Proxima is the easy case. Most of the interesting targets you hear about, exoplanets and habitable zones and so on, are tens, hundreds, or thousands of light years away. At Apollo speeds, or even at faster but still realistic fractions of light speed, those trips are not journeys. They are multi-thousand-year projects that outlast entire civilizations. At this point, you might say, okay, then we don't visit, we just talk. We use radio. That moves at light speed, so conversation should be fine. That feels like a good workaround until you check how far your own radio bubble has actually reached. Humans have been sending strong radio signals into space for a little over a century, mostly unintentionally through things like broadcast TV, early radar, and other high-power transmissions. Light travels about 1 light year per year, so after about 100 years, your we exist sphere has a radius of roughly 100 light years. A sphere 100 light years across sounds big, but compare it to the Milky Way. The galaxy is around 100,000 light years wide. That means your radio bubble covers a tiny patch, only about 1,000th of the galaxy's diameter. In terms of volume, since volume rises with the cube of the radius, your bubble fills a minuscule fraction of the galaxy. Inside that 100 light-year radius are maybe a few thousand stars. The Milky Way has at least 100 billion stars, maybe more, so only a tiny fraction of potential listeners have even had the chance to receive your earliest signals, and that assumes they were listening with sensitive equipment, pointed in the right direction at the right time. Then there is signal strength. Radio waves spread out as a sphere, so the same power is spread over a larger and larger surface as distance grows. Every time you double the distance, the power per square meter drops by a factor of 4. At tens of light years away, normal TV and radio leakage from Earth is buried under background noise. To pick it up, aliens would need either ridiculous antennas or very lucky circumstances. In practice, the only truly noticeable signals are narrow, high-power beams we deliberately aim out, and we have sent very few of those toward very specific directions in the sky. So if a civilization is just a bit beyond that 100 light-year radius, or if they were not tuned in at exactly the right time, they literally have no way to know that you are here yet. From their point of view, your planet might as well still be a quiet ball of rock and water with no radio chatter at all. And the same logic applies in reverse. Their early noise would also spread and fade, and your current detectors might not be good enough or pointed correctly to catch it. Now, put this together with distance and ask a harder question. What happens if your nearest intelligent neighbor is not 10 light years away, but 1,000 light years away? That is still a very small fraction of the galaxy's size, but it completely destroys the idea of conversation. If you send a message at light speed to someone 1,000 light years away, it takes 1,000 years to arrive. If they reply immediately, their answer reaches you 1,000 years after that. One question, one answer, 2,000 years gone. On human timescales, that's basically never. No language, no culture you know today lasts that long in a stable form. Even your species' entire written history fits inside a window shorter than 6,000 years. So you cannot have back and forth discussions, you cannot negotiate, you cannot share urgent warnings or coordinate projects. At best, you send one-way messages into their far future, and they send one-way messages into yours. Both of you are talking to descendants you will never meet. In that situation, the word neighbor stops behaving like it does on Earth. A neighbor on Earth is someone you share time with, someone who hears your noise while you're making it, someone you can visit or at least call and get an answer within minutes. Across 1,000 light years or 10,000 light years, none of that is true. Even if you and some other civilization exist at the same time, and even if you both point antennas at the sky, the speed of light stretches every possible interaction into something that feels so slow that it no longer fits any normal idea of contact. So when you combine the huge distances with this absolute speed limit, you get a simple, harsh result. Even if there is intelligent life fairly nearby on a galactic map, your physics turns that near into effectively never. You share a galaxy, but you do not share a present tense, and that pushes you toward a much darker conclusion for the next step. Because if travel is almost impossible and conversation is stretched over millennia, then the whole galaxy itself starts to look less like a crowded city and more like a giant structure where each small region is mostly empty, with stars spread so far apart that almost all of them will never host a pair of civilizations that can notice each other at the same time. You live in a galaxy that really is like a huge city of stars, but your address is basically in the quiet suburbs, far from anything that feels busy or crowded. The Milky Way, the galaxy you're sitting in right now, is roughly 100,000 light years across. From one edge of the disk to the other, light itself, moving at 300,000 kilometers per second, would need about 100,000 years to cross it. The main disk is only about 1,000 light years thick, so compared to its width, it's a very flat structure. In straight distance, that width is around 950 quintillion kilometers, and something like 590 quintillion miles. Your entire civilization, every city, every person you know, sits on a planet orbiting one star in one tiny patch of that disk. So you might hear huge city of stars and picture a dense glowing street packed with lights, like a sci-fi skyline. But that picture is wrong in a very important way. How crowded is this galactic city really if you zoom in where you actually live? The truth is, stellar crowding, at least in your part of the galaxy, is mostly a myth. Movies and games usually show stars so close together that you see hundreds of bright suns jammed into the sky. In reality, in the region around the sun, the average spacing between stars is a few light years. That means your nearest stellar houses are separated by trillions of kilometers. Use Proxima Centauri again, roughly 4.24 light years away. That's about 40 trillion kilometers, about 25 trillion miles between our sun and the closest other star. Imagine every home in a city being separated by that kind of distance. You wouldn't call that crowded, you would call that almost completely empty. Even in the thicker parts of the disk, most of space is just vacuum, with occasional stars sprinkled through it. There are regions like globular clusters or the galactic center where stars really are packed more tightly, but you don't live there. In your sky, the stars look close because your eyes collapse 3 dimensions into a flat plane. On a map that respects the real distances, every star is isolated by sheer emptiness. So when people say there are so many stars, there must be so many civilizations, they skip over the fact that each of those stars is sitting in its own enormous bubble of nothing. So where exactly are you inside the structure if it's so big and so empty, and does that position help or hurt your chances of having neighbors? Your sun orbits the center of the Milky Way at a distance of around 26,000 light years. You're not near the central bulge, where the star count ramps up dramatically. You are out in one of the spiral arms, in a region called the Orion Arm or Orion Spur, a minor arm between 2 bigger ones. Think of it this way. If the galaxy were a city, the core would be the dense downtown, full of traffic and chaos, and you would be living a long train ride away in a calm residential zone with fewer buildings and fewer lights. That has pros and cons. Near the center, you get a higher density of stars and heavier elements, which is good for building planets, but you also get more supernovae, more intense radiation, more gravitational disturbances, and a massive black hole dominating the dynamics. That is a dangerous place for fragile biospheres that need billions of years of relative stability. Out where you are, supernovae are rarer. Giant collisions are less common, and the environment is more stable over long timescales. The trade-off is obvious. You get safety, but you also get distance. And that distance doesn't just separate you from violent events, it also separates you from potential loud civilizations. You might think, fine, maybe that just means we're in a quiet star neighborhood. But over time, as we orbit, we pass by new regions. Maybe we eventually sweep past someone else's patch. So how fast are you actually circling the galaxy, and how often do you return to the same kind of location? The sun takes on the order of 250 million years, a quarter of a billion years, to complete one full orbit around the center of the Milky Way. That is your galactic year. In that time, Earth goes around the sun 250 million times. The last time your solar system was roughly in this part of its galactic orbit, dinosaurs were dominating the planet. No humans, no cities, no radio, just long extinct ecosystems walking around under the same band of stars. This matters for neighbors because it shows you how rarely you share an epoch with anyone. If it takes 250 million years to do one lap, and any given technological civilization might only exist for, say, 10,000 or 100,000 years before it changes, collapses, or evolves into something totally different, then the odds of another civilization lining up with you both in space and in time are terrible. They would have to be close enough in the same spiral arm, active during the same tiny slice of that 250 million year orbit, and also at a compatible technological level for two-way contact to even make sense. So you do not just lack neighbors because of distance, you also barely share the same when with anybody. Another civilization could have risen and fallen 2 galactic blocks away, a few million years before your ancestors even climbed out of the trees, and you would only ever see the silent physical traces, if you see anything at all. Their signals could still be moving, but by the time they cross those light years, the senders are gone, and you are listening to a history that can never answer back. Put all this together and the picture gets sharp. You live in a galaxy that's enormous, thin, and mostly empty. The average separation between stars is so big that each one is functionally isolated. Your own star sits far from the central chaos, in a quiet spiral arm, where conditions are good for stability but bad for dense clustering of civilizations. And your entire orbit around this structure is so slow that you rarely, if ever, cross paths with anyone else who happens to be active at the same time. On a map, the Milky Way looks crowded. On the scales that matter for contact, it's sparse, slow, and brutally indifferent to your urge for company. And that's just inside your home galaxy. The real pressure starts to build when you zoom out even further, because once you stop thinking one galaxy and start looking at groups of galaxies, superclusters, and the huge empty gaps between them, you realize the Milky Way itself is just a small island inside an even larger, mostly silent structure. Zoom out, your whole galaxy is just one node in your local group, and those groups themselves are spread out over ridiculous distances. On the largest scales where gravity still wins over expansion, your address isn't just the Milky Way, it's something called the local group. That's your immediate cosmic district. The local group is a small cluster of galaxies, anchored by 2 big ones, the Milky Way and Andromeda, plus the smaller Triangulum galaxy and a few dozen dwarf galaxies. All of them are gravitationally bound to each other, which means their mutual gravity is strong enough to keep them in the same overall region, even while the universe expands. The scale here matters. The local group stretches over a few million light years, roughly 3 to 5 million light years across. That's not poetic language. That is literally your neighborhood size. Inside this local district, you jump from galaxy to galaxy in units of millions of light years. So even the galaxies that count as your close companions are separated by gaps a million times bigger than the distance to Proxima Centauri. You already know 4 light years is bad for having neighbors. Now your home cluster uses millions of light years as the basic step on the map. So here's a question. If a whole galaxy with 100 billion stars is just one node in your local group, what does that do to your odds of anyone being close in any useful sense? Next level out, the local group isn't just floating alone. It's part of a larger pattern of galaxy groups and clusters. The local group sits on the edge of something called the Virgo supercluster, a much larger structure, tens of millions of light years across. The Virgo cluster itself, near the center of that region, has thousands of galaxies packed into a volume that on a human map would just look like a tiny smudge. For a while, astronomers thought Virgo supercluster was the big picture, but it turns out even that is just a piece of an even larger flow of matter, a giant region we call Laniakea, which in Hawaiian means immense heaven. Laniakea spans something like hundreds of millions of light years from end to end. Within it, matter is not randomly scattered. Galaxies and clusters flow along gravitational valleys toward common attractors. It's like a gigantic drainage basin for galaxies, except instead of water falling downhill, whole clusters are drifting through space under the pull of dark matter and gravity. Every cluster inside that region may host thousands of galaxies, and every galaxy may host billions of stars, and the huge fraction of those stars may have planets. That sounds like a recipe for a universe that should be packed with life. But there's the catch. If your large-scale neighborhood is tens or hundreds of millions of light years across, then even a nearby intelligent species might live not just on another planet or another star, but in another galaxy altogether. That's already beyond anything you can realistically cross, even at a good fraction of light speed, within the lifetime of any civilization you can currently imagine. And the space between these big structures is where the picture gets even harsher. Between the filament of galaxies, there are huge regions called cosmic voids. These are not just slightly empty areas. They are enormous, underdense bubbles in the matter distribution of the universe, spanning tens to hundreds of millions of light years with almost no galaxies in them at all. The typical density inside a void can be orders of magnitude lower than the cosmic average. A few lonely galaxies might drift through, but for the most part, these are just giant volumes of almost pure nothing. So think about the layout now. You have clusters of galaxies, like the local group, sitting along filaments which feed into larger superclusters like Virgo, all part of a still larger Laniakea region, and between these threads and nodes are monstrous areas where there's basically nothing to talk to. If you dropped a technological civilization on a galaxy deep inside a void, they could look in every direction and see almost no other galaxies close by. They would be isolated from the cosmic web even more than you are. If they pointed radio telescopes outward, the odds of finding anyone nearby would be even worse than yours. So here's the uncomfortable twist. Even if life is common, most of the physical volume of the universe is structured so that almost all of it is just empty dark space, either within galaxies between stars, or between galaxy groups, or inside these massive voids. The real pattern is not a crowded 3D grid of civilizations. It's thin strands and dense nodes of matter wrapped around hollow regions where nothing much happens. Underneath all of this is one main builder: gravity, plus dark matter setting the scaffolding. Dark matter does not interact with light, but it does feel gravity, so over billions of years it clumps into a huge web of filaments. Ordinary matter, the stuff that makes stars and planets and you, falls into those same structures. Where the dark matter density is high, you get galaxies and clusters. Where it's low, you get voids. On the biggest scales, the universe looks like a network of bright islands connected by long strands, with vast, empty oceans between them. Now, bring expansion back into the picture. The universe is not just sitting still while this structure exists. Space itself is stretching. On small scales, inside gravitationally bound systems like the local group, gravity wins, so the expansion does not pull those galaxies apart. But between superclusters, and especially across the gaps between the big filaments, expansion dominates. That means the islands are not drifting closer, they're effectively drifting farther apart. Given enough time, more and more of them slide past the kind of horizon where their light will never reach each other again. So if life sparks on one of these islands, a galaxy in one filament or cluster, and also sparks on another island far away, the space and expansion between them are so large that in practice they might as well be locked in separate universes. No message can realistically bridge that gap. No physical ship can ever cross it and come back with news. The only connection is that they share the same laws of physics, but not a shared history, not a shared conversation. So now your situation looks like this. You live in one galaxy, in one modest group of galaxies, sitting inside a supercluster embedded in a larger flow, surrounded by gigantic voids and separated from other similar regions by distances so large that far doesn't really capture it. Gravity has built you a cosmic archipelago, not a single continuous continent of matter. And on an archipelago this spread out, with islands slowly pulling apart as the universe expands, even a universe full of life can feel functionally empty, because almost every thinking species that exists will never know the others are there. And this is still before you really account for time, because all of these structures evolve over billions of years, and individual civilizations blink on and off over tiny slices of that timeline. When you stack long distances on top of short lifetimes, the chance that two intelligent species share not just the same universe, but the same region and the same era drops even further. Even if the universe is full of life, there's a real chance you've already missed almost all of it, and whatever comes after you will miss you as well. The problem now isn't distance, it's timing. The universe is about 13.8 billion years old. That's 13,800 million years of history before you. If you compress that whole timeline into a single 24-hour day, the first simple life on Earth shows up pretty late. Complex animals even later, and humans like you appear in the last few seconds before midnight. Every city you've ever built, every language, every bit of technology, all of that fits into a razor-thin slice at the very end of that day. So here's the key question. If your entire technological phase so far is just a few seconds at the end of a 24-hour universe, what are the odds that some other civilization's few seconds line up perfectly with yours? Think about how long a technological species might actually last. Right now, you have one data point, us. We've had radio for just over 100 years, industrial civilization for maybe a couple of hundred, organized societies for a few thousand. Even if you're optimistic and say a typical technological species manages to survive in some recognizable high-tech form for 10,000 years, or even 100,000 years, that is still tiny compared to 13.8 billion years. 10,000 versus billions is like a single frame in a long movie. Even 100,000 years is still less than 1% of 1% of the universe's age. Two civilizations could live in the same region of the galaxy, even orbit similar stars, and if their technological windows are separated by just 1,000,000 years, they will never overlap. One might rise, expand a bit, send some probes, then collapse long before the other even crawls out of its own stone age. To each of them, the galaxy will look empty and quiet, even though in reality, they took turns in the basic patch of space. They're not separated by distance, they're separated by when, and that gap is enough to erase any chance of direct contact. Now stack light travel time on top of that. Say there is or was a civilization about 1,000 light years away from you. That's still a small fraction of the Milky Way's 100,000 light year width. If they sent out a powerful radio signal or a laser beacon, that signal takes 1,000 years to reach you at light speed, about 9.46 quadrillion kilometers, roughly 5.9 quadrillion miles. If their civilization collapses or goes extinct today, you won't know for another 1,000 years, because their last emissions are still in flight. From your point of view, they look alive, broadcasting, active. From their point of view, they are already gone. The same logic applies the other way around. Your own radio noise, TV, radar, everything, is forming a bubble only about 100 light years in radius right now. If humanity disappears tomorrow, future listeners out there, 1,000 light years away, will still see and hear you for centuries or millennia after you're gone. They will be listening to ghosts, to signals from a species that no longer exists. So even in the best case, where someone is out there and you both send signals, the delay is so large that any conversation you have is between different eras, different versions, or entirely extinct civilizations. So now your uncomfortable twist: how do you build a real relationship with anyone in the universe? By the time their message gets to you, they might already be history. And by the time your answer gets back, your own civilization might just be a layer in the rock. And this is where the James Webb Telescope makes things even more uncertain. JWST has been looking at the very early universe, and what it's seeing is not a slow, gentle buildup of structure. It has found surprisingly massive, bright galaxies and early galaxy clusters in the first few 100 million years after the Big Bang. These objects seem more mature, more chemically enriched, and more organized than standard models predicted for that era. In plain terms, it looks like stars and galaxies formed, merged, and evolved faster and more violently than we thought. If the universe built large, complex structures earlier than expected, that could shift the timeline for when planets with heavy elements like carbon, oxygen, silicon, and iron became available. Those elements are crucial for rocky planets and for the kind of chemistry life uses. Maybe habitable planets were possible much earlier than we assumed, or those early environments might have been too extreme, with intense radiation and frequent supernovae repeatedly sterilizing young worlds. Either way, your previous neat picture of life must start roughly here in cosmic time is on shaky ground. So now you have two big uncertainties stacked together. First, you don't know how often life appears and becomes technological, or how long those technological phases last. Second, you're learning that your models of when and how fast galaxies and stars form might be off by a lot. That means your guesses about when life tends to arise in cosmic history could also be wrong. You might be very early, one of the first waves of intelligence in this part of the universe. You might be very late, a leftover in a region where most civilizations came and went long ago. Or you might simply be in a quiet time slot between busier eras when not much is happening near you. Either way, timing is brutal. Distance already makes neighbors unlikely. Add the fact that civilizations probably live through short, unstable technological flashes inside a universe that is billions of years old, and still surprising you with how fast it built its structure. And the odds tilt even more toward this outcome. Most of the intelligent life that ever existed will never share a present with you. You pass each other like ships in the night, not because you don't exist, but because your windows of awareness barely overlap. And that makes the next piece even more important, because if you can't rely on timing and you can't rely on distance, you start looking at something else: the actual planets and their environments. You want to know how many worlds even have the basic conditions for life, and whether the thousands of exoplanets we've found so far are a sign of company or just a reminder that sampling a huge galaxy with a tiny set of tools can still leave you effectively alone right where you are. We've found thousands of planets, and your brain wants to relax and say, okay, so the galaxy must be full of potential neighbors. But statistically, at this point, that's almost the same as finding none. Right now, astronomers have confirmed on the order of 6,000 exoplanets, and there are thousands more strong candidates waiting to be confirmed. That sounds like a lot when you say it fast. It's more planets than you could ever list by name. But then you put that number next to the estimated hundreds of billions of stars in the Milky Way, and the scale mismatch hits you. 6,000 out of, say, 200 billion is like sampling a tiny pixel on a giant screen. You haven't mapped the galaxy, you've barely scratched it. So here's the uncomfortable question. With a sample that thin, can you honestly say anything strong about how common or rare Earth-like worlds really are near you? Most of the exoplanets you've heard about are found by one main technique, the transit method. You stare at a star for a long time and watch its brightness very precisely. If a planet's orbit lines up just right, it will cross in front of the star from your point of view, block a tiny bit of the light, and create a small dip in brightness on a repeating schedule. Measure that dip, measure how often it repeats, and you can infer the planet's size and orbit. That sounds clean, but the geometry is brutal. For a planet to transit, its orbit has to be aligned almost perfectly edge-on with your line of sight. If the orbit is tilted just a bit too much, the planet never passes in front of the star from Earth's perspective. It still exists, it still orbits, but your method is blind to it. So the set of planets you can detect with transits is only a narrow geometric slice of what is really there. It's like trying to count all the cars in a huge city by standing under a single street lamp and only counting the cars that pass exactly behind that lamp from where you stand. The ones that pass slightly to the left or right or use a parallel road are invisible to your method. They still exist, they still matter, you just never see them. So when you say, we found 6,000 planets, what you really mean is, we found 6,000 that happen to be in the very specific orientations and conditions our methods can see. And that's before you look at another bias, what kind of planets your tools actually like to find. Current detection methods are strongly tilted towards weird systems, not calm Earth-like ones. The transit method easily finds big planets close to their stars because they block more light and they go around quickly, so you see multiple transits in a short mission lifetime. These are hot Jupiters, mini Neptunes, and super-Earths hugging their stars in very tight orbits. The radial velocity method, which looks at the wobble of the star due to the planet's gravity, also favors massive planets in close orbits because they yank harder on the star and produce a larger, faster signal. Your own solar system would actually be hard to detect with those tools if you were looking from far away. Jupiter would show up eventually, but Earth at 1 astronomical unit with a 1-year orbit and a small size would be subtle. You'd have to watch for a long time with very stable instruments and catch multiple transits or a very faint wobble. So it's no surprise that your current catalog is full of big, close-in planets that don't look like home. The methods are doing exactly what physics pushes them to do. They find what's easiest first. So when people say, we haven't found Earth 2.0 around the nearest stars, maybe there's nothing out there, they're skipping over the fact that your search is still heavily biased and incomplete. You surveyed only a tiny fraction of stars with the precision and duration needed to pick up true Earth analogs, and even then in certain orientations. Not seeing something under those conditions is not strong evidence that it's rare. It's mostly evidence that you're still in the very early phase of the search. This is the crucial point. No Earth twin detected nearby yet is not the same as no Earth twin exists nearby. It means your current telescopes, your current time baselines, and your current methods are still primitive compared to the scale of the problem. You are trying to judge the layout of a galaxy-sized city by checking a handful of apartment windows and a couple of streets. The honest conclusion is not, we're alone around here, it's, we don't know yet because our sampling is tiny and skewed. But that also cuts the other way. You cannot safely say, look, 6,000 planets, so life must be everywhere and neighbors must be common, because the sample is too small and too biased to support that too. You don't know how many of those worlds have stable climates, long-lived atmospheres, protective magnetic fields, or the right chemistry for biology. You don't know how often life, once it starts, climbs all the way up to complex technological forms. So you're stuck in an uncomfortable middle. Your data is strong enough to prove that planets are common, but not strong enough to tell you how many good ones are close to you. And in terms of neighbors, planets are common is only the first filter. You still have to pass the filters of habitability, the origin of life, the rise of complex life, the evolution of intelligence, and the survival of technology, all stacked on top of each other. This leads to a simple but heavy question. If thousands of known exoplanets are still too few and too biased to answer who's near us, and if the methods that would find Earth-like neighbors are only just coming online, what does that do to your search timeline? It means you are still at the very beginning. You have enough evidence to know the galaxy offers many possible homes. You do not have enough resolution to tell if any of those homes near you are actually occupied. So when you look out and see no clear Earth twin next door, the safe conclusion is not there's no one around, it's our instruments are early, our techniques are limited, and our sample is tiny. The absence you see is more about your tools than the universe. And once you realize that, the next question gets sharper. Even if the right kind of planets are out there, how many of them are actually friendly to life as we know it for long enough that two civilizations in the same region have any chance of overlapping in time? Even if planets are common, the ones that actually stay habitable are picky, fragile, and probably rare. Being in the right star system is not enough. You need to be in the right orbital zone, with the right kind of star, with the right planetary setup, and you need all of that to hold together for billions of years. That's a lot of filters stacked on top of each other. Start with the basic one you hear all the time, the habitable zone. Around a sun-like star, there's a range of distances where a planet with the right atmosphere can keep liquid water on its surface. For the Sun, that band is roughly from about 0.95 to about 1.37 times the Earth-Sun distance. In kilometers, that's around 140 million to 205 million kilometers from the star. In miles, about 87 million to 127 million. Move a planet much closer than that, and it risks runaway heating, boiling oceans, and a thick, choking atmosphere. Move it much farther out, and surface water ends up locked as ice, and the planet becomes a frozen desert. So the first problem is simple. The Goldilocks ring is a thin band, not a huge safe zone. Shift your orbit by tens of millions of kilometers, and you can move from liquid water as possible to permanent ice or permanent steam. That's before you even ask what kind of atmosphere the planet has, how reflective its clouds are, or how much greenhouse gas it carries. You can put two planets at the same distance from the same star, and one can be comfortable, while the other is hell. So just being in the habitable zone is necessary, but not nearly enough. You might think, fine, as long as we find planets in that temperature band, we'll have a lot of potential neighbors. But now you have to look at the star itself. Many of the most common stars near us are red dwarfs, smaller and cooler than the Sun. Their habitable zones are much closer in, sometimes only a few % of the Earth-Sun distance. That sounds convenient because it means habitable planets would be easier to spot. But these stars have a problem. They flare hard. Red dwarfs can throw out huge bursts of ultraviolet and X-ray radiation, along with charged particles, far more frequently and violently than the Sun. A planet that sits in the right temperature zone around one of these stars might still be under constant attack from these stellar tantrums. Over time, those flares can strip away the atmosphere, especially if the planet's magnetic field is weak. Once the atmosphere thins, liquid water becomes unstable, and surface life has a rough time. So you could have nearby neighbors in terms of distance, but their worlds might be locked into harsh, unstable conditions that never allow complex life to take hold on the surface. Even around a stable star like the Sun, you then run into planetary roulette. A habitable planet needs enough mass to hold on to an atmosphere, but not so much that it becomes a gas giant. It needs a molten core that can power a magnetic field, which helps shield the surface from high-energy particles and solar wind. It might also need plate tectonics, the slow motion of crustal plates driven by internal heat to recycle carbon and regulate the climate over long timescales. Earth happens to tick all those boxes. It's massive enough to keep a decent atmosphere, it has a liquid outer core generating a magnetic field, and it has active plate tectonics that help regulate carbon dioxide over hundreds of millions of years. Now, compare that to Mars and Venus, which share the same star. Mars is too small. It cooled faster, lost most of its magnetic field, and its atmosphere thinned out. It may have had rivers and lakes early on, but now it's a cold, dry world with a thin air layer. Venus is almost Earth's twin in size and distance, but something in its early climate and atmosphere history tipped it into a runaway greenhouse. Its surface is now hotter than a kitchen oven, with crushing atmospheric pressure. Same star, similar distances, completely different outcomes. Out of 3 rocky neighbors, only one ended up with long-term surface habitability. Then there's the timing problem again, now combined with habitability. Stars don't stay the same forever. Over billions of years, a star like the Sun slowly brightens. As it does, the habitable zone moves outward. A planet that starts in the comfortable band can find itself getting too much energy later on. Water can slowly evaporate, carbon cycles can break, and the planet can move out of the safe zone even if its orbit never changes. Scientists sometimes talk about the continuously habitable zone, the range where a planet can stay in good conditions for a long stretch of time, not just visit temporarily. For Earth, the total window of being comfortably habitable might be on the order of a few billion years. It's already used a large chunk of that. In a billion or so from now, as the sun keeps brightening, conditions on Earth are expected to get much tougher for complex life, even if nothing else goes wrong. This means any given planet only has a finite slot where complex life and technology can realistically appear and function. A few 100 million years too early, and the planet might still be too unstable. A few 100 million years too late, and the climate might already be sliding into extremes. Now, put that back into the question of neighbors. For you and another civilization to exist near each other and at the same time, a lot has to line up. Both of your stars have to have planets in their habitable zones. Those planets need the right mass, magnetic fields, and geological activity. They need to avoid being sterilized by giant impacts. They need to hold a stable climate for a very long time. Then life has to start, climb all the way up to intelligence, and build technology. And all of that has to happen while both planets are still in their habitable windows and while they're close enough for any chance of communication. So, if you're waiting for aliens to answer our broadcasts, here's the hard truth. Almost no stars have even heard us ring the doorbell yet. Human beings have only been loud in radio for a bit over a century. Early broadcast radio, TV, radar systems, military communications, big scientific transmitters, those started going into space around the 1920s and 1930s. Since radio waves move at light speed, about 300,000 kilometers per second, roughly 186,000 miles per second, that gives us a we exist bubble with a radius of only about 100 light years right now. A sphere 100 light years across sounds big until you compare it to the Milky Way. Within that 100 light-year radius around the sun, you might have a few thousand stars, maybe tens of thousands if you're generous with estimates. The Milky Way has at least 100 billion stars, maybe a few 100 billion. So our noisy bubble currently covers far less than 100,000th of the galaxy. And in terms of volume, which scales with radius cubed, the fraction is even smaller. That means almost every star in the Milky Way and almost every potentially habitable planet has not yet had any chance at all to detect that your species even exists. And that's the optimistic view, just counting geometry, not sensitivity. Radio waves don't stay strong as they travel. They spread out as a sphere getting larger and larger over time. The total energy is the same, but it's smeared over a bigger surface. Every time you double the distance from the source, the energy per square meter drops by a factor of 4. Go 10 times farther, the power per square meter drops by a factor of 100. So take a TV signal that's strong near Earth, powerful enough to hit a rooftop antenna clearly. By the time that signal has spread out to a distance of a few dozen light years, the power per square meter is tiny. At tens or hundreds of light years, the signal is weaker than the natural radio noise from stars, gas clouds, and the cosmic microwave background. It becomes a whisper, buried inside a loud static hiss. To pull that out, an alien civilization would need a huge collecting area, extremely sensitive receivers, and they'd have to be staring at our exact patch of sky at the right frequency for a long time. And even then, they might only see a faint statistical bump, not a clear "this is a TV show" pattern. So yes, the radio bubble is 100 light years in radius, but the part of that bubble where our random leak signals are actually strong enough to be easily picked up is much smaller, more like a tight shell around Earth. Beyond that, those emissions are technically there, but so diluted that they are right at or below the detection threshold, unless someone is really, really trying. That's why realistic interstellar contact almost certainly doesn't happen by accident through random leakage. If you actually want to talk to someone, you don't just rely on your planet's background chatter. You use deliberate, high-power, narrow beams. You pick a target star, you tune a frequency, you point a big antenna, and you transmit for a long time. That concentrates energy in a tight cone instead of spraying it in all directions. The power at the receiver end can be orders of magnitude higher than any casual broadcast. We have done this a few times with things like the Arecibo message and a handful of other directed transmissions. Those were sent toward specific star clusters or nearby stars as demonstrations, not as part of a continuous galaxy-wide communication strategy. The total number of stars we've actually addressed on purpose is tiny, and the time windows for those beams were short. Most of the sky has never been pinged by a serious sustained signal from Earth. From the galaxy's point of view, we've flicked a few laser pointers for a moment, then gone back to mostly talking to ourselves. So when you think we've been broadcasting for 100 years, why hasn't anyone answered? The answer is straightforward. Almost nobody has had the chance to hear you, and almost none of your emission is optimized for being heard. It's like standing in a huge stadium, mumbling under your breath, and expecting someone on the far side in a random seat to notice and shout back. Now flip the perspective. If other civilizations are at our level or only a bit more advanced, their situation is probably similar. Their early radio and TV equivalents would also be weak, broad, and quickly drowned out by distance. Their stronger signals, if they use them at all, would be narrow beams aimed at specific directions they care about, not everywhere. If they don't happen to aim at us, we won't see them. If they aim at us, but only for a short window, and we're not looking at the right frequency at the right time with enough sensitivity, we miss it. On top of that, there's the time factor again. Maybe a civilization's radio loud phase only lasts a few centuries or millennia before they switch to communication methods that are harder to detect externally, like fiber, tight beam lasers, or tech we haven't even thought of. That means there's only a narrow observational window during which their leakage is detectable. If their noisy era was 1,000,000 years ago, their signals might have passed by before our instruments were switched on. If their noisy era begins 1,000,000 years from now, we're simply early. So when you look at the sky with our current telescopes and radio arrays and say we haven't heard anyone, it's silent, what does that really prove? It doesn't prove the galaxy is empty. It doesn't prove we're alone. It mostly proves that our ears are still small, our listening time is short, and our search space is huge. You've only scanned a tiny band of frequencies over limited patches of sky for a few decades, with sensitivity that is still improving step by step. This is the key point. The silence you hear right now is not strong evidence of solitude. It's evidence of how early and how limited your search still is. If you turn on a radio for 10 seconds in a city and don't catch any specific station because you're between channels, you don't conclude the city is empty. You conclude you didn't listen long enough, or on the right bands, or with a good enough antenna. The same logic applies here, just scaled up to light years and billions of stars. But there's a darker version of that conclusion too. Even if your radio bubble grows, even if you build bigger telescopes and send more powerful beams, all of that still only extends your reach by a tiny fraction of the galaxy at any given time. The combination of weak leakage, narrow beams, huge distances, and narrow time windows means that most civilizations that ever exist will probably never know each other through radio at all. They'll live and die under quiet skies, just like you see now. And while you're wrestling with that, you also have to accept another uncomfortable limit. Even if your telescopes get much better and your radio ears get bigger, there's a hard cap on what you can actually see. You can already detect galaxies more than 13 billion light years away. You can watch the universe in its early stages. But none of that lets you zoom in and see the city lights or radio towers on the nearest exoplanet. Your instruments are powerful, but they are not magic microscopes for civilizations. They see stars and gas and dust at huge distances, but not people. So the next step is to confront that mismatch directly. Your technology lets you see incredibly far, but not incredibly finely. You can spot a galaxy in the early universe, but you can't see whether the nearest potentially habitable world has continents, oceans, or artificial signals on its night side. That gap between reach and detail is another reason why you might have neighbors in principle while still being stuck with nothing but silence and distant anonymous dots of light. Our best telescopes can see galaxies more than 13 billion light-years away, but they still can't show you the city lights on the nearest exoplanet. That mismatch is important. You have instruments with insane reach, but very limited detail, and that keeps you blind to almost everything that actually matters for the "are we alone nearby" question. Take the James Webb Telescope. JWST is picking up galaxies like MOM Z14, whose light left them almost 280 million years after the Big Bang. That's extremely early, when the universe was less than 3% of its current age. In distance terms, that's light that has been traveling for over 13 billion years across expanding space to finally hit JWST's mirrors. You can measure their brightness, their rough size, their redshift, and even get hints about the elements in them. You're basically looking at the universe as a baby. But notice what you're actually seeing there. You see galaxy shapes, clumps of stars, gas, dust. You do not see individual planets, let alone any sign of life or technology. Those early images tell you when and how structures formed. They don't tell you who, if anyone, ever lived on any given world. You can be incredibly good at reading the universe's baby photos and still know almost nothing about the actual tenants on any given planet. Now, drop the distance down to something that feels local on a cosmic map, say 10 light years. That's about 95 trillion kilometers, roughly 59 trillion miles. That's very close by galactic standards. Even there, the problem is resolution. An Earth-sized planet at 10 light years away has an angular size so tiny that in most current telescopes, it would be smaller than a single pixel. You don't see a little blue and green sphere with continents and weather. You see, at best, a dot that occasionally dims its star's light by a fraction of a percent, or a tiny wobble in the star's motion. So from that dot, what can you really get? You can estimate its size, its orbital distance, maybe its rough temperature. With very careful observations, you might pass starlight through its atmosphere during a transit and get a crude spectrum. That spectrum can tell you if there are gases like water vapor, carbon dioxide, methane, maybe oxygen, but you're still dealing with averages. You don't see coastlines, you don't see forests, you definitely don't see roads or megacities. Even on the nearest potentially habitable planets, our best gear can't directly show people. It can only show indirect markers in a single pixel of light. That's why the search for technosignatures is such a big deal. Instead of hoping to see cities, you look for side effects of technology that might be visible at interstellar distances. That could be strange combinations of gases in an atmosphere, like large amounts of industrial chemicals that don't stay stable for long without continuous production. It could be waste heat patterns that don't match natural processes. It could even be artificial illumination, like faint glow on the night side of a planet brighter than you'd expect from reflected starlight alone. The reality today is that we're just starting to do this seriously. Instruments are only now reaching the sensitivity needed to sniff atmospheres on small exoplanets around nearby stars. Detecting a subtle technosignature like a trace industrial compound in a spectrum that faint is at the edge of what we can do. Looking for night-side lights is even harder because you're trying to separate a tiny signal from the blinding glare of a host star over light years of distance. This is early-stage, bleeding-edge science. Not seeing a clear techno signature yet doesn't mean none exist. It mostly means we're just turning the equipment on and learning how to use it. So when you hear no signs of alien technology found so far, be careful about what that really implies. It doesn't mean we checked thoroughly and it's empty. It means we've only just begun to look with instruments barely capable of scratching the surface over a very limited sample of stars. You've checked a few nearby systems in limited ways, not the galaxy in any comprehensive sense. There's also a practical detection horizon for these kinds of searches. The farther away a planet is, the harder it is to get enough photons from it to build a detailed spectrum, or to separate its light from its star. For life-related features, like oxygen, methane imbalances, or other biosignature gases, you're mainly looking at nearby systems, tens of light years away. With future, much larger space telescopes and advanced coronagraphs or star shades, you might push that out to hundreds of light years. But you're not going to be characterizing the atmospheres of planets on the other side of the galaxy anytime soon. The signal drops off, and practical mission lifetimes limit how wide and how deep you can survey. So, put this in concrete terms. Say with the next couple of generations of telescopes, you can do serious life and techno-signature searches out to maybe a few hundred light years. That's still only a small bubble in a galaxy 100,000 light years wide. If no one lives in that radius, or if any civilizations in that bubble are either extinct already or not yet at a detectable tech level, then all your instruments will show you is a set of quiet, anonymous worlds. Meanwhile, the rest of the galaxy and the rest of the universe could have plenty of life, and even plenty of intelligence, just all outside the range of your current microscope. So the real situation is this. You can see extremely far in space and time. You can watch galaxies form and merge across billions of years, but you can't zoom in on the nearest Earth-like world and simply check occupied or empty. Your reach is huge, your detail is tiny. That gap keeps you locked in uncertainty. You might be surrounded by life that is effectively invisible to your current tools, or you might genuinely be isolated in your local few hundred light years. Right now, you can't tell the difference. And that brings up an even sharper point. Maybe the problem isn't just your instruments, maybe it's also your location. On top of all these limits, you might not even live in the busiest part of the galaxy. Some regions are richer in stars and heavy elements, but they're more violent. Other regions, like where you are calmer and safer, but also more spread out and quieter. So the next question is very direct. What if the part of the galaxy that's best for life to survive long-term is also the part where potential neighbors are naturally few and far between? The safest place for life in the galaxy may also be the place where you're least likely to get neighbors. When you zoom out and look at the Milky Way as a whole, not every region is equally friendly for long-term, complex life. Some zones are better at building planets and stirring things up, others are better at letting fragile ecosystems sit in peace for billions of years. The problem is the quiet zones are also the emptier ones. Start with the inner galaxy, near the center. As you move inward toward the galaxy core, the number of stars per unit volume goes up. The gas there has been recycled through many generations of star formation and supernovae, so it's rich in metals. In astronomy, that means any element heavier than hydrogen and helium. More metals generally means more solid material to build rocky planets. So on paper, the inner galaxy looks like a great place if you want a lot of planets. More stars, more planets, more chances for life, right? But the inner galaxy comes with serious downsides. High star density means more supernovae, more gamma-ray bursts, and more powerful radiation events overall. When a massive star explodes within a few tens of light years of a habitable planet, it can strip away a big chunk of its ozone layer, flood the surface with high-energy particles, and trigger mass extinctions. Near the center, these events are more frequent. You also have the central supermassive black hole and a more chaotic gravitational environment, with stars passing closer to each other, disturbing orbits and comet reservoirs. Over hundreds of millions of years, those disturbances can send more comets and asteroids into the inner regions of planetary systems, raising the impact rate on any habitable worlds. So you get this trade-off. Lots of stars, lots of metals, lots of planets, but also a harsher environment with more ways to reset or sterilize complex life before it gets very far. Great for star formation statistics, not so great for letting a biosphere sit quietly and evolve intelligence without being repeatedly kicked in the teeth. Now move outward, away from the center, into the galactic disk where we are. As you go farther out, the density of stars drops. Fewer stars per cubic light year means fewer nearby supernovae, less intense background radiation, and a calmer gravitational environment. That's good if your goal is to keep a planet's orbit stable, reduce catastrophic events, and give life a long, unbroken window to get complicated. This part of the galaxy is more like a low-traffic region. Big disruptive events still happen, but less often. The downside is obvious. Fewer stars means fewer planetary systems in any given volume. The gas out here has also gone through fewer cycles of star formation and explosion, so the metallicity, the abundance of heavy elements, is lower than in the inner regions. That can mean fewer rocky planets per star, or different distributions of planet types. So while an individual star out here might be safer for long-term habitability, there are simply fewer stars to work with. That means fewer rolls of the dice when it comes to producing a technological species. Some astronomers take all of this and talk about a galactic habitable zone, a band in the Milky Way where conditions balance out in a way that's reasonably good for complex life. Not too close to the center where radiation and chaos are high, not too far out in the extreme outer disk where heavy elements are too scarce and stars are very spread out. In this picture, there's sort of a ring where metallicity is high enough for planets, but danger levels are low enough for long-term stability. When you plug in what we know about the Sun's position, Earth looks like it sits roughly inside that ring. For us, that's good news. It helps explain why we have a rocky planet at a comfortable distance from a relatively stable star in a region that hasn't been wiped clean by constant supernova blasts. It suggests that, at least from a galactic point of view, our address is not terrible for building and keeping a technological civilization. But that same just right ring has another implication. It's structurally similar to a quiet suburb. You're not packed in with neighbors, star density is moderate, explosions are rarer. Things are spread out. And this is where the safety versus neighbors trade-off becomes sharp. All the factors that help your planet survive for billions of years, being far from the most chaotic regions, living in a zone with moderate star density, sitting in a fairly stable orbit around a long-lived star, also cut down the chances that another technological civilization is sitting very close by. If you move the sun much closer to the galactic center, your sky would have more bright stars, but your risk of sterilizing events would go up. If you moved it much farther out, you might avoid some dangers, but you'd also lose metals and dense star fields that help produce lots of planets. So when you say we picked a good spot, the next question is, good for what? It's good for survival, good for long-term evolution, good for not getting hit by constant catastrophic blasts, but it's not good for packing lots of possible civilizations into the local area. The safest zones are the ones where stars and habitable worlds are relatively far apart. Survival and solitude end up linked. To get one, you often accept more of the other. Now, combine that with everything you've already seen. The galaxy is big and mostly empty. Distances between stars, even in this habitable ring, are measured in light years. The speed of light is a hard limit. Civilizations have short technological windows compared to the age of the galaxy. Habitable planets are narrow targets in both space and time. And the region that gives you the best shot at a stable biosphere spreads those targets out even further. Put it all together and the conclusion is blunt. If you live in a galactic habitable zone, the odds are high that you're in a safe but low-density environment. That raises your chances of existing at all, but it lowers your chances of having someone at roughly your level of technology sitting within easy communication distance. You got the long, quiet runway you needed to appear, but you probably didn't get a crowded neighborhood. And that's just for talking. If you start asking what it would take to actually go and visit anyone who does make it through all these filters, you run straight into the next wall, the energy cost of interstellar travel. Because even in the best, safest ring of the galaxy, with the friendliest possible setup, the physics of moving real ships between stars is so demanding that nearby civilization turns into basically unreachable as soon as you start doing the numbers. Even if you somehow find a nearby civilization, actually getting there is a physics and engineering nightmare. Up to now, you've been dealing with distance, timing, and habitability. Interstellar travel adds a new layer, raw energy cost. The moment you stop thinking about sending a message and start thinking about sending a ship, the numbers hit you hard. Start with what you actually have today. Chemical rockets. The best chemical rockets you've built can push a spacecraft to speeds of a few tens of kilometers per second. Take a round number, about 15 kilometers per second, roughly 34,000 miles per hour. For getting around the solar system, that's respectable. It got humans to the moon, it sends probes to the outer planets. It's not trivial. But stack that against interstellar distances and you see how weak it really is. 1 light year is about 9.46 trillion kilometers, around 5.9 trillion miles. If you try to cross that at 15 kilometers per second, you can do a simple ratio, total distance divided by speed. You end up with a travel time of roughly 20,000 years for just 1 light year, and that's ignoring acceleration and deceleration. Proxima Centauri is about 4.24 light years away, so at that speed, you're looking at something like 80,000 to 90,000 years of flight time. That's longer than your entire species has had agriculture. That's not a mission, that's a geological era. And that's the idealized case, where you assume you can instantly accelerate to cruise speed and never slow down. In reality, you have to ramp up speed without crushing your crew with too many G's of acceleration. Then at the other end, you have to slow down, otherwise you just blow past the target star. The longer you take to accelerate gently, the longer you spend time not yet at top speed. On top of that, chemical rockets have to carry their own fuel, and the amount of fuel grows explosively as you ask for higher speeds, because of the rocket equation. Very quickly, you hit a wall where most of your vehicle would have to be fuel just to push a tiny payload. And even then, the trip still takes tens of thousands of years. So you move the conversation to advanced ideas, fusion drives, antimatter engines, beamed light sails. These concepts, at least on paper, could get a craft up to a decent fraction of light speed. People often talk about 10% of light speed as a target. 10% of light speed is about 30,000 kilometers per second, around 18.6 million miles per hour. Compared to chemical rockets, that's incredible. Now, Proxima Centauri at 4.24 light years away becomes maybe a 40 to 50 year trip from the point of view of an outside observer, plus time to ramp up and slow down. Suddenly, a single human lifetime can, in theory, span an interstellar journey. But look at what you're asking for. To get a reasonably sized ship to 10% of light speed, you need enormous energy. Kinetic energy scales with the square of velocity, so going 10 times faster needs 100 times more energy per unit mass. For a ship that weighs thousands or tens of thousands of kilograms, the total energy is comparable to years of current global energy production concentrated into one vehicle. You also have to keep that engine running reliably in deep space, handle waste heat, and protect the crew or payload from radiation. Then there's the environment between stars. At 10% of light speed, tiny dust grains and gas atoms become dangerous. Hitting even a small grain at that speed releases energy like an explosion. So you need shielding, which adds mass, which demands more energy to accelerate, which demands bigger power systems, and the loop continues. Decelerating at the destination is equally tricky, unless you're willing to treat the mission as a one-way flyby or rely on the target system to help you slow down with its own beams or magnetic fields. Projects like laser-pushed light sails, think of a very lightweight probe with a large reflective sail pushed by a powerful laser array from home, try to dodge some of this by sending tiny packages there quickly. But even those concepts need energy levels and engineering that are way beyond what you've actually built. And they solve only part of the problem, getting a tiny package there quickly. They don't solve communication delay, and they definitely don't make it easy to send whole communities of living beings. Now, place that against human timescales. An average human life is maybe 70 to 80 years. Social systems and technologies tend to turn over on timescales of decades. Even at 10% of light speed, a trip to a star 10 light years away takes around 100 years from launch to arrival, once you include realistic acceleration and deceleration. That's already longer than a single lifetime. A slower ship at 1% of light speed drops the energy cost but stretches the trip to about 1,000 years. So right away, any serious interstellar mission to even nearby stars starts to look like a multi-generation project. You either send generation ships where people live and die on board and their descendants arrive, or you send frozen embryos, or you send only machines. In every case, you have to maintain hardware, life support, and social stability over time spans longer than any continuous institution your species has ever run. You're not planning a voyage, you're planning a self-sustaining micro-society in a hostile environment for centuries. Now, add the challenge of coordination. If you launch a ship to a star 10 light years away, you then have a 10-year communication lag in one direction, 20 years for a round trip. Any decision that requires back and forth with home takes decades. If the trip itself takes centuries, the world that launched the ship will be completely different by the time it arrives, if it's still there at all. Systems change, priorities shift, languages evolve. It becomes almost impossible to keep a tight, real-time connection between the travelers and the origin civilization. The mission is effectively cut loose, with only slow, delayed updates at best. Then ask the obvious question. If just reaching a star 10 light years away is this hard, what about 30 light years, or 50, or 100, where any nearby civilization is statistically more likely to be? Even at 10% of light speed, a 50 light year trip takes on the order of 500 years. A round trip is about 1,000 years, not counting stays. That's 1,000 years of hardware survival, of shielding, of cultural continuity, or of purely robotic operation without catastrophic failure. You are in the territory of civilizational commitment, not exploration tourism. When you combine distance, energy, and time, you get a simple but harsh conclusion. Even if there is intelligent life within a few dozen light years, the odds that both sides develop the technology, the energy infrastructure, the will, and the long-term stability to send large, crewed ships to each other are tiny. Maybe ultra-advanced civilizations could manage it, but for most, the cost-benefit calculation is brutal. It will usually be easier to send probes or stay home and work on local megastructures than to be a species that routinely swaps residence with other star systems. So yes, you might share a galaxy with other intelligences in theory, but in any realistic human sense, you don't share a neighborhood you can walk across. The physics is stacked against large-scale mingling. You get at best a trickle of slow probes and delayed signals, not a bustling interstellar community. And all of this still assumes the universe just sits there and lets you try. It doesn't. On the largest scales, space itself is expanding, and that expansion is accelerating because of dark energy. The more you look at that, the more you realize that the set of places you could ever, even in principle, reach or receive signals from is shrinking over cosmic time. If potential civilizations aren't already close, the universe is actively pushing most of them farther and farther out of reach. The universe isn't just big, it's getting bigger faster, and the farther any life is from you, the more permanently it's being pushed out of your reach. This isn't a slow drift you can eventually outrun with better rockets. It's built into the way space itself behaves on the largest scales. First thing to get straight. Expansion isn't just galaxies flying away through empty space like bullets from an explosion. On large scales, the distances between unbound galaxies increase because space itself is stretching. The metric that tells you how far apart two distant points are is changing with time. Galaxies that are gravitationally bound to each other, like the ones in your local group, stay together because gravity wins locally. But galaxies far enough apart, not bound into the same group, get carried away from each other as the overall fabric of the universe expands. So when you hear this galaxy is receding from us, that doesn't mean it fired its engines and took off. It means that the amount of space between you and it is increasing. The farther away the galaxy is, the faster it appears to recede, because there is more expanding space in between. That's why you can have distant galaxies with recession speeds greater than the speed of light without breaking relativity. Nothing is moving faster than light through space locally. The space between you is just growing fast enough that the total separation increases faster than light can bridge it. This expansion is also the reason your observable universe has that 46.5 billion light-year radius, even though the universe is only about 13.8 billion years old. Light from very distant regions started traveling toward you billions of years ago when they were much closer. As that light moved, space in between kept stretching. By the time the photons arrive at Earth today, the galaxies that emitted them are much farther away than the distance the light actually traveled in a straight line at a fixed scale. So you see them as they were more than 13 billion years ago, but their current distance is roughly 46.5 billion light-years. Here's the key part. That observable radius is not a fixed wall. With time goes on, light from slightly more distant regions have time to reach you, so in one sense your visible bubble grows. But at the same time, dark energy, the thing driving accelerated expansion, is pushing the universe into a regime where there's a different kind of limit, an event horizon. Regions far enough away recede so quickly that light they emit now will never catch up to you, no matter how long you wait. They are outside your future light cone forever. So you end up with two facts that sound contradictory but aren't. You can still see some very distant galaxies whose ancient light is just arriving now because that light started out long ago. But there is also a growing set of regions from which no new light, emitted now or later, will ever reach you. As cosmic time continues, more and more of the universe slides across that horizon. You get a last look, and then that region's future activity is permanently hidden. Project this forward and the picture gets bleak. In the far future, trillions of years ahead, most galaxies outside your local group will have redshifted so much that they effectively vanish from view. Their light will be stretched to wavelengths so long and diluted so much that even perfect detectors won't pick them out above the background. More importantly, even if you had ridiculous propulsion, you could never actually reach them. The expansion of space would carry them away faster than any ship could close the gap. That faster-than-light recession is allowed precisely because it's space expanding, not objects breaking the local speed limit. From the point of view of distant civilizations sitting in their own galaxy groups, the same thing happens. To them, your group drifts away, fades, and eventually crosses their event horizon. They lose the ability to see you, and they lose the ability to ever send a signal or a ship that could arrive. Every gravitationally bound island in the cosmic web ends up isolated, each one surrounded by an empty, expanding ocean of space. So in the deep future, the only galaxies that remain visible and reachable from here are the ones bound into your own little cluster, basically the Milky Way, Andromeda, and the smaller galaxies of the local group, which will eventually merge into a single large galaxy-like object. Everything else will be gone from view and gone from reach. That is the end state if dark energy keeps behaving the way it does now. That has a brutal implication for the idea of cosmic neighbors. Any potential friends don't just have to be close in space and overlapping in time, they also have to be within the same gravitationally bound region as you before expansion pulls the rest away for good. The set of places that can ever exchange matter or information with you is not the whole observable universe. It's whatever shares this gravitational island with you and remains bound as dark energy takes over. Within that island, you still face all the old problems: huge distances between stars, limited travel speeds, short technological windows, narrow habitable zones. Outside that island, physics is basically telling you no forever. No matter how advanced a civilization becomes, they don't get to chase down galaxies that have already slipped beyond the event horizon, because the gap between them grows faster than any signal can close. So your realistic pool of possible neighbors shrinks again. It's not the thousands of galaxy clusters you can currently see with telescopes. It's the few dozen galaxies in your local group, and realistically, the subset of those where conditions for complex life actually line up. Maybe that's still a big number. Maybe it's very small. Either way, the rest of the universe is on a countdown to permanent disconnection. And there's another layer of uncertainty on top of all this, even inside your reachable island. Your models for how structure formed and when galaxies and stars assembled keep getting updated. The more JWST and other observatories look into the early universe, the more they find things that don't quite match the neat timelines you expected. If your basic picture of when heavy elements formed, when galaxies settled, and when conditions became good for life is off, that means your estimates of where and when neighbors could appear are also off. In other words, the universe is not only shrinking your long-term contact list through expansion, it's also hinting that your whole mental map of where life should cluster might be wrong in important ways. And that could be one more reason why, in your local patch, no one seems to be home. Every time you push the instruments a bit deeper, the universe turns out to be stranger and maybe harsher for life than the models said it should be. You're not just refining details anymore, you're seeing big pieces of the story shift, especially in the early universe. And that matters a lot for the "are there any neighbors near us" question. Start with one of the clearest surprises, how fast structure seems to have formed. Standard models said that right after the Big Bang, the universe went through a long, slow buildup. Tiny fluctuations in density grew, dark matter clumped, gas fell into those clumps, and over hundreds of millions of years, you first get small galaxies, then bigger ones, then full clusters with lots of members and hot gas between them. Galaxy clusters, the really big, massive systems with many galaxies bound together and filled with X-ray emitting gas, weren't supposed to be common extremely early on. Then JWST started looking. It has picked up objects that look like already assembled, or at least rapidly assembling, massive galaxy clusters around the billion years after the Big Bang. That's very early, less than 10% of the universe's current age. And yet you're already seeing the signatures of deep potential wells full of galaxies and hot gas. That means structure in the universe grew faster and more efficiently in some regions than a lot of models had assumed. The cosmic web came into focus earlier. Gravity, plus dark matter, pulled things together aggressively. At the same time, JWST has been finding ultra-bright, compact early galaxies, like MOM Z14, with light that left them only about 280 million years after the Big Bang. These galaxies are small in size but insanely active. They pump out light far more intensely than you'd expect from their age and mass, and some show signs of being more chemically enriched, meaning they already contain heavier elements than theory predicted for that era. Heavy elements come from stars that live and die. To get a lot of them early, you need rapid cycles of star birth and star death packed tightly together. Put those clues together and you get a picture of a young universe that's not calm at all. It's a place where gas collapses quickly, stars ignite in huge numbers, and massive stars go supernova on short timescales. Fast early star formation means lots of massive, short-lived stars, which turn into supernovas, black holes, and intense radiation fields. Those events flood surrounding space with high-energy photons and particles, shock waves, and strong winds that can blow gas out of galaxies or strip atmospheres off early planets. So instead of a gentle cradle where young galaxies slowly and quietly build stable environments, the early universe looks more like a period of violent overactivity. Gas clouds light up, blow themselves apart, fall back, and repeat. Black holes feed and throw off jets. Radiation levels around active regions can be extreme. That's great for creating the heavy elements you eventually need for rocky planets and biology, but it's not obviously great for letting fragile, complex biospheres sit undisturbed on planetary surfaces. Now think about what that does to your sense of when life can reasonably arise and persist. If early galaxies and clusters are more massive, more active, and more chemically enriched sooner than you thought, then the timing for when good planets appear shifts. Maybe habitable planets with the right elements show up earlier than you expected. Maybe large regions get sterilized repeatedly before they ever settle down. Both possibilities change your estimates. You also have to account for the fact that dense early environments are likely full of close supernovas and energetic events that can damage atmospheres or strip ozone layers. Even if planets form early, they might not get the kind of long, stable climate window that Earth had. Or maybe only certain pockets, shielded by geometry and distance, stay relatively calm. That would mean life-friendly environments are not just rare in space, they're rare in specific epochs and specific corners of the cosmic web. The bigger point is this: if your models of when galaxies assemble, how fast they enrich themselves with heavy elements, and how intense their early star formation is keep getting revised, then every downstream estimate is also on shaky ground. Things like typical time when rocky planets become common, average radiation environment in a galaxy at a given age, and how long stable habitable zones last are all tied to that structure formation story. If that story is wrong or incomplete, your guesses about how frequently life-friendly environments arise and how long they last are not reliable. So when you look around your local patch now and see no obvious neighbors, be careful about assuming that's a random fluke. It might be, but there's another possibility. The way the universe actually builds its structure, fast early clumping, violent starbursts, strong feedback from black holes and supernovas, changing metallicity over time, might naturally create large regions and long periods where complex life is likely unlikely, and only a few relatively quiet pockets where it can realistically appear and last. If that's true, then no one near us stops being a surprise and starts looking like exactly what you should expect from this combination of cosmic history and local conditions. You live in one particular galaxy, at one particular radius, in one particular epoch, after a long chain of violent events gradually calmed down enough to give your planet a stable run. There's no guarantee that same calm phase happened nearby in sync with you, or that it produced civilizations right next door. And that loops you straight into the core tension people keep coming back to, the Fermi question. When you look at the raw numbers, billions of galaxies, hundreds of billions of stars per galaxy, your brain jumps straight to, it would be crazy if we were alone. But when you unpack them, you get a very different picture, where we might be alone in our local area is not a dramatic claim, it's the cautious one. Start with the raw numbers. The observable universe may contain anywhere from a few 100 billion to a few trillion galaxies. A typical galaxy, like the Milky Way, has on the order of 100 billion stars. Even if you lowball everything, you still end up with a ridiculous number of stars overall. Then you add what we've already learned from exoplanet surveys. Planets are common. Many stars have planets. Many systems have multiple planets. Just multiplying those big counts together, your first reaction is understandable. Statistically, you feel like someone should be near. But that first reaction is using a very naive filter. Star exists, life exists, intelligent life exists, technological civilization exists near us. Reality is not that simple. Between a random hydrogen cloud and a radio-capable species, there are many steps where things can stall or fail. At each step, the fraction of systems that make it through can drop dramatically. These are what people mean when they talk about filters, and some of them could be great filters, steps that are extremely hard to pass. List a few obvious ones. You need stars that are long-lived and stable. You need those stars to have planets, and not just any planets, but rocky planets in the right temperature zone. Those planets need to hold on to liquid water and a decent atmosphere over billions of years. They need to avoid constant sterilizing impacts and radiation events. Life has to start at all, which we still don't know how easy or hard that is. Simple life then has to climb to complex multicellular life. Complex life has to evolve intelligence. Intelligence has to develop technology. And then that technology has to survive its own risks long enough to spread or become visible. You don't need every one of those steps to be brutally hard for neighbors to be rare. If just one or two of them are extremely unlikely, that's enough. For example, if life starts easily but complex multicellular life is rare, then most habitable planets will stay at the single-celled level forever. If complex life is common but technological intelligence is rare, then most biospheres just fill up with animals and plants that never build radios. If intelligence is common but long-lived technological civilizations are rare, then most species wipe themselves out or stall at low-tech stages before they can spread or be detected. The real problem is that right now, you don't know which step, if any, is the great filter or where it sits. You have exactly one world where you've watched the full chain play out from life appears to global technology. That's Earth. You have one example of life, one example of intelligence, one example of a technological civilization. That's all. Trying to infer galactic statistics from that is like trying to infer global climate from one thermometer. You can guess, you can build models, but you can't be confident. You might look at Earth's history and say, life started pretty early once the planet cooled, so maybe abiogenesis is easy. But that's one timeline. Maybe Earth is a lucky outlier. You might say, complex life took billions of years to appear, so maybe that step is hard. Or maybe Earth just had unusual delays. You can't separate luck from general rules with a sample size of one. The same uncertainty applies to the technological phase. Is it typical for a species to get radio and industry for a few centuries and then either stabilize or disappear? Or are we a weird case on a much broader distribution? You don't know yet. So when people use the raw star and galaxy counts to argue neighbors must be everywhere, they're taking a huge shortcut. They're acting as if all the filters are easy by default, and you have to justify why any of them would be hard. But the data doesn't support that confidence. Given what we actually know, the honest position is that several steps in the chain could be very tough, and we don't know which ones yet. Now, fold in all the other constraints you've already seen. The galaxy is large and mostly empty. The speed of light caps communication and travel. Habitable zones are narrow in both space and time. Civilizations have short technological windows compared to the age of the galaxy. The region of the galaxy that is safest for long-term life is not where stars are most densely packed. Dark energy is gradually cutting off your access to most of the universe, and early universe data suggests the environments that eventually produced you came out of a long, violent, highly structured history, not a uniform, friendly background. In that context, what does everybody even mean? There could be many civilizations scattered across the full observable universe, but almost all of them could be too far, too early, too late, or already gone for you to ever have a practical interaction. On the scale that matters for you, a few tens to a few hundreds of light years, the question is much narrower. Are intelligent technological civilizations common in this specific small volume of the Milky Way right now? Given the filters, the timing issues, and your tiny sample size, assuming yes, there are plenty, we just haven't seen them yet, is actually the bold claim. It assumes that all the hard steps are easy, that many civilizations survived their early technological phases, that they happen to be in your region, and that their active window overlaps with yours. It also assumes they either constantly broadcast strong signals or build huge detectable structures that you've simply missed by bad luck. The more conservative, data-driven stance is the opposite. It says maybe there are many civilizations in the universe overall, but the probability that one of them is both nearby and active at the same time we are is low. Under that view, we might be alone in our immediate neighborhood is not a pessimistic guess. It's the default position until we see actual evidence otherwise. You don't promote there are neighbors within a few hundred light years from science fiction to serious claim without data to back it. That doesn't mean you resign yourself to never searching, it just means you don't let the huge size of the universe trick you into thinking neighbors are guaranteed. The size also multiplies the number of ways things can fail to line up. Distance, time, filters, habitability, expansion, all of them work together to thin out the set of worlds that end up close enough, alive enough, and synchronized enough to say hello. And that brings you to the last uncomfortable shift in perspective. If the cautious answer is that we're probably rare in our sector, then the silence around you isn't just a disappointment, it's a sign of how statistically strange it is that you exist at all. That changes what your situation means. Instead of being one civilization among many chatting in a busy galaxy, you're more likely to be one of very few, possibly the only one in this whole region with the ability to understand the universe and change it. Which leads directly into the final piece of the story. If we are alone nearby, that's not just lonely, it's a kind of promotion. It means this small patch of space-time is effectively ours to shape or to destroy, and no one else is coming to correct our mistakes. If there's no one near you, that's not just lonely, it's a promotion, whether you like it or not. Out of a universe maybe 93 billion light-years wide in diameter right now, with hundreds of billions of galaxies and ridiculous numbers of stars, you happen to be on a small rocky planet at about 150 million kilometers from a stable star, roughly 93 million miles, with liquid water on the surface, complex chemistry in the crust and oceans, and nervous systems that are aware enough to ask these questions. That alone is already statistically extreme compared to the default state of the universe, which is hydrogen and helium drifting in cold, dark space with no one to count anything. If you zoom out, almost everything you see is empty. Huge volumes of space are just vacuum, with a few particles per cubic meter. Even inside galaxies, the average separation between stars is light years, trillions of kilometers, trillions of miles. On top of that, most places and times are probably either too hot, too cold, too short-lived, or too unstable for complex life to build up and survive. Against that background, you are sitting on a world that has had liquid water for billions of years, a relatively calm radiation environment, plate tectonics recycling carbon, and a runaway feedback loop of brains building tools and systems. So here's the first hard point. In raw probability terms, you are already part of an insanely specific event. You are not a typical random atom. You are part of a small group of atoms that can think about the rest. If nearby space is really empty of other minds, that doesn't make you less special. It makes you more rare. And rare things have consequences, because if they break, they don't get replaced easily. Now add the second point. If there are no advanced civilizations in your immediate region, there is no one older and wiser to hand you a guidebook. No one has sent us a clear, verified list of do this, don't do that for planetary scale technology. No one has shown up with a record of how they handled their own climate transitions, resource limits, or existential risks. There is no galactic instruction manual hidden in the sky. There is no cosmic customer support line that fixes your atmosphere if you trash it. That means every big step you take, nuclear power, bioengineering, AI, geoengineering, asteroid mining, all of it, is being done as a first attempt, with no confirmed examples to copy. Maybe somewhere else in the universe, someone already figured out what works and what doesn't. But if they're too far away or long gone, their solutions are not going to land in your inbox. You are running the experiment live on the only known habitable planet in range. So here's the question that follows. If there are no older siblings nearby to bail you out, who exactly is supposed to keep this place on track if you don't? Look at it in terms of territory. Within a few light years of the sun, as far as we know today, there are no other minds at all. Just gas, dust, rocks, and simple physics. Extend that radius to a few dozen light years, you get more stars and more planets, but still no confirmed signs of intelligence. Push it to a few hundred light years, your instruments are still blind to any clear signals from civilizations at our level. So for all practical purposes, this chunk of the galaxy, this small segment of a spiral arm, these local stars and their planetary systems are under the control of exactly one technological species, us. That doesn't mean we own them in some legal sense. It means we are the only ones here with any realistic chance of understanding them and influencing their future. We are the only ones here who can map these systems, send probes, reroute asteroids, or change planetary surfaces on purpose. If anything meaningful is going to be done with this patch of spacetime, we are the ones who will do it, or fail to do it. So when you talk about our local patch, you're not just talking about Earth. You're talking about the Moon, Mars, the outer planets, near-Earth asteroids, and in the longer term, maybe some of the nearest stars. If no one else is nearby to compete or cooperate, then by default, this entire zone is our responsibility to understand, and if we expand, to manage. We are the only lab technicians on duty in this part of the cosmic experiment. That leads to the last piece, loneliness as responsibility. If we are alone nearby, then what happens on Earth is not just another small story in a crowded universe. It's the only version of this story that this region of the Milky Way is getting, at least for a very long time. If we wipe ourselves out, or lock ourselves into a permanent low-tech state, or slowly let our planetary systems degrade, this corner of the galaxy may go back to being just physics and chemistry, with no one to notice or care. That changes the weight of your choices. Climate policy, energy systems, war and peace, space exploration, all of that stops being only about human comfort or national interests. It becomes about whether this patch of space-time ever develops long-term, stable intelligence that can last for millions of years, not just thousands. It becomes about whether the stars near us ever have probes sent to them, whether distant future beings ever look back on this era as the start of something, or the one and only attempt that failed. So when you stand under a clear night sky and feel that silence, it might not be the silence of an empty universe. It might be the silence of a universe that, in this sector, has handed the microphone to you and is waiting to see what you do with it. No one else is speaking here, not because they don't exist anywhere else, but because in this region, right now, you are the only ones with a voice. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.